Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 10th, 2026, about 5 days ago. It introduces a low-cost gripper and a control framework called ReTAF that achieves a 68% stable grasp rate on fragile objects, compared to just 44% with standard position control. The paper is titled, Learning Force-Regulated Manipulation with a Low-Cost Tactile Force-Controlled Gripper. And as we'll see later, the results for handling delicate items like potato chips are really impressive. Alright, Figure 1 illustrates the high-level motivation here. At the top, we see examples of everyday objects like strawberries and potato chips that require careful handling. Panel A shows how humans manage this. We combine visual perception with tactile feedback to apply just enough force for a gentle grasp. Then in Panel B, the robot mimics this process. It takes visual data of the object and readings from tactile sensors, processes them through a network, and outputs a specific motor force, like the 0.8 newtons shown here. So, Table 1 compares this new hardware against mainstream commercial options to explain why a custom build was necessary. If you look at the prices on the right, standard grippers typically run between $2,000 and $6,000. Furthermore, the middle column shows that most of them have a high minimum force, starting around 10 or 30 newtons, which is often too rough for fragile items. In contrast, the TF gripper at the bottom costs just $150 and can regulate force down to 0.45 newtons. Okay, Figure 2 demonstrates why that low force control matters so much in practice. Here, the authors compare standard position control on the left against force control on the right, applied to potato chips and cherry tomatoes. In the top section, look at the green bars representing a stable grasp for two slightly different chips. With position control, the safe window is extremely narrow and shifts based on the chip's exact size, which makes it very easy to crush or drop them. However, on the right, force control maintains a wide, consistent, stable region between 0.1 and 1 newton for both chips, proving it is much more robust to small variations. Well, having established the need for better control, Figure 3 breaks down the low-cost hardware design they built to achieve it. At the top in Panel A, we see the key mechanical parts, like the motor and pulley assembly, which drive a timing belt to ensure smooth transmission. The main photo in Panel B shows the fully assembled unit on a robot arm, utilizing a 3D printed structure to keep costs down. Then on the right, Panel C highlights the sensing, combining a wrist camera for vision and a 32x12 tactile sensor array embedded in the soft fingertips. So, with the hardware ready, Figure 6 presents the control framework, known as ReTAF. The system splits the job into two distinct parts to handle the speed difference between vision and touch. In the top panel, the base policy uses camera views to handle arm movement and decide when to open or close the gripper, running at a relatively slow 1 to 15 Hz. Then, in the bottom panel, the force adaptation policy takes over during the actual grasp. It combines wrist images with tactile sensor data to adjust the gripping force 30 times a second, providing the high-frequency reaction needed for delicate objects. Alright, Figure 8 validates this approach by comparing force predictions over time against a human demonstration. The snapshots at the top show the robot grasping a cherry tomato, while the chart below tracks force across the task phases. Notice how the green dashed line for ReTAF closely follows the blue ground truth line. In contrast, the red dashed line for the diffusion policy drifts significantly and misses the release timing. This confirms that the tactile feedback, shown by the purple curve spiking at contact, is essential for stable regulation. Wrapping up, two main takeaways stand out. First, low-cost hardware, like the TF gripper, effectively democratizes force control research. Second, separating high-frequency tactile feedback from slower visual planning is key for handling fragile items. This brings us closer to robots that can safely handle delicate groceries without crushing them. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.